Hi, so we're back and we now start the course in earnest, right? So this is still part of the background, so to speak, to the course, but it's important to review the background. Some of this I've mentioned in problems at problems at zero, which is what some of you requested, very sensibly, I might add. Uh, And so this, before getting into the details of the matter, just to give you a broad idea of what we're going to be talking about, this is about how we get from a particle description to a macroscopic, and I put the macroscopic in double quotes. I'll tell you why and so on and so forth. Okay. In other words, do we really want to? So, as I've stated repeatedly earlier, a plasma is defined as a collection of charged particles. Okay, say positive charges, negative charges, another positive charge here, another negative charge here, so on and so forth. Lots of them. Okay, so these are the constituents. Lots and lots of them. Now, are we gonna? And obviously, these charges are gonna, exert forces on each other. They will undergo collisions. A positive charge here and a negative charge here. If this guy, if the negative charge is moving past the positive charge, it would be attracted towards it, right? It would be attracted towards it. And on the other hand, if there was a positive charge, it would be, and it was trying to move towards it, it would be repelled, right? So either way, there are forces, and so they are subject to these particles are subject to collisions. And as such, the fact that particles are subject to collisions, this aspect is similar to gases, to neutral gases. Okay, but what we're going to be talking about right now, so what we're going to be talking about to begin with does not specialize to the fact that, does not necessarily consider the fact that these particles are charged. Okay, we might as well be talking about just uncharged particles, just a collection of neutral atoms, and they're all subject to collisions. Now the question is, are we going to are we going to follow each particle around to follow the dynamics of each particle? That's one way. Okay. Or are we going to resort to going for some kind of coarse graining? And I will underline the some kind of coarse graining. Well, as with everything in physics, it depends. The answer is it depends. It depends upon what level of detail we want to do, what kinds of time scales, or what kind of phenomenon we want to investigate. Okay, so the coarse graining you can think of as, well, you've got a collection of particles, right? So in the if we have a really you've got a collection of particles like so, and if you've got if your magnification, how do you draw a lens? I mean, that's what I want to do. Okay, so this is a lens, So if your lens is really large, you are able, you're not doing any coarse graining at all. You are seeing, or your lens is really powerful, you're seeing, every particle, and you will be following the dynamics of every single particle around. Okay, so this would be what I would call the microscopic description, so to speak. There is an in-between thing. There's an in-between thing where you are kind of, you're not. I mean, what you observe is a collection of particles. So the lens, I would draw the lens a little smaller. Okay, so there's a large lens, large magnifying power. Here is a smaller lens. You are maybe you're standing a little farther away, or you're employing, as in you are not seeing every individual particle. You are what you're seeing is you're seeing a larger area than just this. You're seeing an area, say, about this big, so that you've got many particles in that area. Okay, but still. What you would be looking at is, I will call this an in-between or a mesoscopic description, okay, where you will be focusing on the distribution function characterizing these particles, like a Maxwell-Boltzmann distribution function, for instance, a velocity and a probability, and you're saying you might say something like this: the most probable velocity, so on and so forth. So in this kind of limit, a distribution function makes sense. Not each individual particle, but a function that tells you, well, I'm most probable. I mean, this is the distribution of velocities of these particles, or temperatures, or so on and so forth. And then the most coarse-grained description would be the macroscopic description. Where really, your lens is really small, and you're seeing an even larger volume than this, and you cannot make out the particles at all. Okay, all you can make out is a sort of, this is the, this, if you will, is the arrow representing coarse graining. So this is the coarsest grain. There's an in-between coarse graining, and this is very fine. Okay, here you see, you deal only with averages. And this is what's called the macroscopic, or I would say, some people call it the continuum description. Here you see, all you can say is, well, I mean, you can characterize, it makes sense, for instance, to talk about a number per centimeter cubed, or an average velocity, or things like that. Okay, density, for instance, a number per centimeter cubed. Here you see, it makes no sense to talk about a number per centimeter cubed. You're looking at the system so close that you are figuring out each individual particle. And here, so what we will do now is try to figure out how to go. What's the general procedure one adopts in going this path. All right, so that's the general philosophy of what we're going to talk about now. And I realize I minimized the wrong thing. Yeah. So now, I call this the kinetic/particle description versus the continuum. And so here I'm talking about only the extremes, this and that. Okay, these two extremes. And roughly speaking, as long as the number of particles in some representative macroscopic volume is much larger than 1, the continuum description is okay. All right, and that kind of makes sense, right? I mean, you have a box, and you have so many particles, so many particles, and so this would be some kind of a macroscopic, representative macroscopic length scale. And so the cube of this would be a macroscopic volume. So essentially what you're able to see here is, and so this fuzz extends all throughout the box. Okay, there's so many particles that you really cannot make out an individual particle at all. Okay, in other words, the number of particles in this representative macroscopic volume is much larger than 1, and much larger than 1 can mean anything from 100 to 10 raised to 6 or any really this much larger is a bit of a subjective thing. In astrophysics, you often tend to skate on thin ice and say if it's larger than 10 or something, let's just go ahead and apply the fluid description. Why? Because the fluid description is much less expensive. Okay, you don't have to follow each particle around computationally. You can only you can afford to simply think about the averages. Okay, right. Alternatively, okay, and for those those of you who've taken my fluids course last semester, this will all be very familiar. These are, I think, essentially the same slides. These few slides. So alternatively, so this is one way of defining it. Alternatively, the mean free path for collisions between particles, like this, given, so this would be lambda. And the macroscopic length scale would be something like this. So if the lambda is much less than L, okay, there's so many of these particles buzzing around inside a macroscopic length scale that it's okay to resort to a continuum description. Okay, to think about the collection of particles as a continuum with a well-defined particle density, with a well-defined average velocity, if there's any, and so on and so forth. Okay. Yet another way of looking at it is that, when particles collide, there's a collision time scale, right? A certain time scale over which the particles are interacting, beyond which you can sort of safely say that the particles are quote unquote free of each other, right? So if the time, what I mean by some macroscopic time scale is suppose you were thinking of wave motion or some other physical phenomena that involves a certain time scale, some t, and you've got a collision time scale tau. Okay, the interparticle collision time scale, right? And if the collision time scale is much larger than the macroscopic time scale you're interested in, then it's all right to adopt the continuum or the fluid description. Okay, now the one aspect in which what we are talking about right now is different from neutral fluids is the definition of the mean free path. Okay, in fluids it's simple enough. You can think of hard sphere collisions, for instance. With plasmas, it gets a little more. With a collection of charged particles, it gets a little different and also a little more difficult. We have to deal with what are called Coulomb collisions, and so that's why I've left it at this now. What is the mean free path? And sometimes there's this funny. We might find time to talk about this in the course. There's this aspect called collisionless plasmas, where for some reason the mean free paths are so long. Mean free paths are actually larger than a macroscopic length scale, and yet somehow the fluid description or the continuum description seems to work well. So you have to scratch your head and ask, what is the operative mean free path? Okay, we'll come to all that. Right, so now think of a gas. Now let's move away from talking about from thinking about charged particles for a minute, let's get back to a gas comprising, say, just hard billiard balls. Okay, hard balls like so, each with radius A. Okay, hard balls. And so the collision cross section is obviously just pi a squared, right? And the mean free path would be, and yeah, we implicitly assume that there are so many of these little balls that it's meaningful to talk about density. Okay, if there are just one or two balls like this, it makes no sense to talk about a density of balls, right? It's only when you have many, say about 100 or more balls in a given macroscopic volume, then it makes sense to talk about the density, right? So, let's assume that that is indeed the case, and the collision cross section is pi a squared, and the mean free path would be 1 over n sigma. You can verify this. You can verify that the dimensions are right. And this is really, I mean, this approximate result is really written from precisely these kinds of rough dimensional considerations. And not to scoff at this, because it can really take us a long way, these kinds of approximate equalities. Okay, it can take us a long way, and for the time being, this is good enough for our purposes, for illustrating the principles involved. Right. In an ionized plasma, the collisions, like I said earlier, are not hard sphere collisions, they are Coulomb collisions, which are slightly different in nature, with the collision cross section depending upon the temperature. T4 is simply the temperature in units of 10 raised to 4 Kelvin. Why such a high temperature? Well, I mean, this is in the context of astrophysical plasmas, and it's not unusual to find, but anyway, I mean, that's all right. I mean, you can express any temperature in this unit, even if the temperature is 10 Kelvin. T4 in that case would be 10 raised to minus 3. That's all. Okay, so this formula for the cross section as such is correct for any temperature. It's just written in a unit in units that are convenient for plasmas that are approximately 10 raised to 4 Kelvin. If it was 2 times 10 raised to 4 Kelvin, for instance, this T4 would just be 2. Very easy to plug in the numbers and bring it up. This ln lambda, I'll tell you what it is. We will discuss for the time being. Let's just take this as a formula, right? And so the main thing to notice from this formula, right? The main thing to so if the collision cross section is such is this, then the mean free path turns out to depend very strongly on the temperature. It goes as the square of the temperature, and it goes inversely as the density. ln lambda is just a constant that we will talk about later. Okay, for the time being, just take it to be a constant, which is about, this is about something like 10 to 20. We will discuss this a little later. There are other complications such as charge screening and so on and so forth that we will discuss as we go along, but this is just an illustration of the fact that the collision cross section is, if for instance you put in the classical electron radius, okay, in here, and just said pi times r sub e, where r sub e is a classical electron radius squared, right? And you computed the collision cross section, you would find that the collision cross section for Coulomb collisions between two electrons is very, very different. Okay, by the way, this is for collisions between like species. The cross section for collisions between unlike species is again different. So just to point out that there can be different kinds of collisions, and we do need to be very aware of Coulomb collisions when we are talking about charged particles. Okay, right. Now, having said a little bit about collisions, just pointed out the fact that there can be different kinds of collisions, we will now start talking about the heart of the matter, which is how to derive bulk properties such as, such as this, such as, density and so on, jet density, velocity, and so on and so forth from the kinetics.